Oversimplify it somewhat, string theory attempts to describe all particles in the universe as infinitesimally small and vibrating strings. These strings are then one-dimensional objects and are hypothesized to be the most fundamental objects in the universe. If it is correct, then everything you are, know, see, even think is the product of these strings. Over a century ago, in 1915, Albert Einstein presented his newly formulated field equations to the Prussian Academy of Science. These equations provided a beautiful description of how matter interacts with each other via the force of gravity. They went above and beyond the work carried out by Isaac Newton a few centuries prior and explained gravity at the largest scales in the universe, alongside predicting other phenomena such as time dilation and black holes. Since then, the model has been proven in multiple ways and is considered one of the most important theories in physics. Unfortunately, however, as great as it isn't complete. General relativity, easily one of the most influential contributions to science, still doesn't provide an explanation for how gravity interacts on the scale of particles in the quantum limit. Surprisingly, the force of gravity is the weakest of the four fundamental forces, which is perhaps not what you'd expect given that gravity literally moves planets. But this means that on the smallest scales of all, atomic and subatomic, gravitational interactions are incredibly difficult to detect. All of the four fundamental forces have, or should have, a respective particle that's responsible for their effect. For example, the photon, which mediates the electromagnetic force. Gravity is then predicted to have its own mediating particle called the graviton. But, and again due to that comparative weakness of the gravitational force, actually detecting the graviton is very, very hard to do. So hard, in fact, that currently the graviton remains theoretical only, and is thought to be impossible to observe. And here's where we get to string theory. In the 1960s, string theory began formulation as an attempt to explain how what's known as the strong nuclear force behaves, which is the force responsible for holding hadronic particles like protons and neutrons together. The theory proceeded to develop further in the 1970s, though, eventually attempting to describe all known particles in the Standard Model. It was then in 1974 that the Japanese physicist Tamiaki Yoneya realized that all forms of string theory predicted a massless particle too. What was doubly exciting, however, was that this massless particle behaved exactly as was predicted for the hypothetical graviton. This was monumental as no theory had naturally provided an explanation for the graviton before, and still no other theory has since. It was soon after this that the separate theory of quantum chromodynamics took over from string theory as the leading explanation of hadrons specifically. However, by now, string theory seemingly had bigger fish to fry in physics. Its main purpose shifted, and it became considered as the major contender for explaining gravity on a quantum scale, as potentially the major contender towards a theory of everything. So that's the story behind it, but still, how does string theory actually work? Again, it predicts every particle in the Standard Model at their most fundamental to be vibrating strings, which are assumed to be a Planck length in size, i.e. the shortest measurable distance. These strings are one-dimensional objects, and the frequency of their quantum vibrations is what determines what type of particle the string represents. From a mathematical perspective, the theory is pretty incredible, providing many advancements which have now been applied to numerous other fields of science. On the other hand, from a physical perspective, string theory has historically proven to be a bit of a nightmare. During the 1980s, there were 5 separate string theories formulated, with one particular version of those requiring a mind-blowing 26 dimensions of reality to work. But eventually, in 1995, Professor Edward Witten proposed a new version called M-theory, which unified all 5 of the previous theories into one and predicted only 11 dimensions in total, 10 spatial and 1 time. Meanwhile, there is another string theory, superstring theory, that manages to work with only 9 spatial dimensions predicted and 1 time, 10 in total. Broadly though, what's clear is that all types of string theory require extra, unobservable dimensions. So what or where are these other dimensions? They're generally predicted to be compact, incredibly small, and curled up. But unfortunately, as of yet, no one has been able to consistently explain the geometry of any of them. And so there are essentially infinite ways that these extra dimensions could be described. And, somewhat despairingly, it seems that the more research that's been put into figuring them out, the further string theory has strayed from working. On top of this, there's no clear way to physically test for the presence of string theory's extra dimensions either. So without any mathematical validity or physical observability, the quest has reached a bit of a dead end, arguably and perhaps substantially damaging string theory's reputation and momentum. Today, many scientists then consider string theory to be a premature effort to solve the problem of quantizing gravity. General relativity was considered to be an almost fully formulated theory within just years of its proposal. On the other hand, quantum field theory, the theory that explains how the fundamental particles of the universe behave, was nowhere near as fully developed and formulated until the latter half of the century. String theory might have been like quantum field then, but the difference is that in the decades since they first turned up, quantum field theory has made significant progress, while string theory has floundered and become dormant. There are direct links to be made too. The main principle of quantum field theory is to describe all particles as fields as opposed to them being concentrated point charges. A simplification of this concept would be to imagine all particles as clouds as opposed to smooth balls. Probably the most important offshoot here, however, is something called unaffective field theory. Among other things, this is an intuitive method of making particle calculations without knowing the complete specifics of the physical phenomena they're describing. Effective fields are then free from mathematical restrictions, which in the days of Einstein made quantizing gravity impossible. In the past decade, there has been significant progress on formalizing general relativity as an effective field theory, to finally explain how gravity works at a quantum scale. So what does this mean for string theory? Its past is complex, and its future is a little muddled. String theory hasn't ever really been one singular theory, and there's never been general agreement on which one is best. What's more, many of the researchers who pioneered string models now currently work in adjacent fields and are trying to look at quantum gravity from other perspectives. Tools that work within the framework of string theory are still powerful, however. For example, calculations on how gravitons scatter off each other have been done using entirely string-based methods. Regardless of string theory's seeming failure at producing a singular formal theory of everything then, its achievements and advances in mathematics should not go unnoticed or unpraised. To this day, it still remains the only theory to naturally predict a graviton after all, as opposed to the plethora of rival theories such as loop quantum gravity, which have never achieved the same feat. In modern-day physics, string theory doesn't have the same momentum as it used to, but its impact has still been significant. Beauty can still be seen within it, as it predicts even the highest powers of the universe to be, at their base, simplistic, fundamental strings. As for the future, there's a chance we may someday find a new version of the theory free from the problems of prior attempts. Research today in the field is minimal, but there are still dedicated teams devoted to making progress. It could yet be that we simply don't have the required mathematical tools at the moment, but with time, we might develop them. For some, there's also the chance that string theory will one day solve or contribute to solving some of the other big questions in physics, like uncovering the mystery of dark matter. What do you think will happen? Do you think that at its vibrating, stringy core, this model could still prove to be the answer to everything? Or is there another entirely new theory just around the corner? One